All right, so week after midterm, we're more than half done with this course, and we will have the midterm and assignment 3 graded by the end of the week, so you'll know where you pretty much sit with about 60% of the course over. And so that you know where you need to go for the rest of the course, or if you're past the point of no return. We are going to be starting the next module in this course, and that's module, I think we're on module 10 since this is week 10, and that's file I/O. In fact, it's not a very big module. Not all the modules are created equal. Some of them are longer, some of them are shorter. This is one of the shorter ones. In fact, we'll get through most 90% of it today, and then you'll do a lot of the stuff that I'm going to demonstrate here in lab tomorrow. And it's quite short because you already know what you're doing in some sense. You've already done input and output from the standard input and the standard output. But guess what? Guess what the standard input is? Guess what the standard output is? Both of those things are files. So they're treated in a Unix system as files that you can read from for input or that you can write to for output. The only difference that we're going to be experiencing now is that we're going to be doing input and output with a different kind of file, a file that is stored on an actual disk, right? It's a unit of stored memory, again, usually on disk, but it doesn't have to be. In fact, when two computers communicate over a network, they do so over a socket. Well, what do you think a socket is? It's a file. One end is writing to this file, then it gets transmitted over abstractly, and the other end is reading from that socket file. Directories, buffers, standard input output, those are files. Sockets that are sent over the network, those are files. In Unix, everything is a file. Everything can be treated as a file that you can read from or write to. And files can also be either plain text or binary. For the most part, we're going to be dealing with plain text files because dealing with binary files means that you have some binary format. Binary formats being like image formats, like JPEGs and PNGs and stuff like that. We're not going to deal with those directly. You've already dealt with them directly. Say in some of your hacks, you've dealt with image manipulations. But what we did was we wrote wrapper code around that, so you didn't have to deal with the low-level binary stuff. In fact, we didn't even write that. We brought in a library to do it. If you do have to deal with binary files, media files, images, videos, audio, things like that, it's usually best to bring in a library because they've already implemented the code to deal with those low-level binary representations. So we're not going to deal with that much at a low level. Instead, we're going to deal with plain text files. Now, even with plain text files, you can have a lot of variation in the types of files that you're dealing with. One of the most common ones that we'll be dealing with are CSV files. Do you remember what CSV stood for? Comma-separated value files. You also have TSV, where your separator is tabs and stuff like that. We mentioned that when we did string processing, because one of the applications that we're going to do now is we're going to do file input-output, file processing for files that are CSV files. Alternatively, all of this falls under, by the way, an area called EDI, which is nothing more than electronic data interchange. You want computer A to speak to computer B by passing data to it. Well, you need some sort of a common way of representing that data. One common way of representing, because over here it might be a Java file over here, the Java program that's processing the data, and over here there's a C file that's or executable that's written in C processing the same data. You need a way to communicate back and forth. Now, usually that's going to be a binary file of some sort, but otherwise you have universal formats such as XML, which stands for Extensible Markup Language. It's a way of taking data, representing it as a plain text file, and marking it up to say that this piece of data is related to that piece of data over there, and that this piece of data represents a name, this piece of data represents, say, a GPA or something like that. And it's a way of marking stuff up and giving it meaning, right? And that's what we mean by semantics. It means that you're giving semantics to your data. There's also JSON, which stands for JavaScript Object Notation. It's just a more lightweight way of representing the same data. And to give you an example of these two things, I'm just going to go to json.org here. And here is a JSON file. You see that it's hierarchical, that things begin with opening and closing curly brackets, and then within that you've got data, glossary, and then you've got a key value pair. right? That this is the key, and then this is the thing that it refers to. The thing that it refers to in this case is another object. So the glossary is made up of this collection of data over here. And then you've got title. The title is an example glossary, right? And then you've got a glossary div, and that represents another object, right? And then that object is made up of more pieces of data, until you get down to, say, a list, or in this case, this is an array of data, right? So represented by square brackets and then a comma delimited list. You've got commas everywhere, stuff like that. That's one way of representing data. The exact same stuff represented with XML means that you are using these tags to tag everything up. The glossary, instead of being one string and then a colon to represent the glossary is this thing over here, you've got a tag, and then everything within that tag is the glossary. And then you've got a closing tag, which has is it a backslash or a forward slash? It's a leaning forward slash, exactly. And then it closes that. Every opening tag has a closing tag. So in other words, there's a lot of redundancy here. And that's why we say that JSON is a little bit more lightweight. You're transmitting a lot less data over a network. You are processing a lot less data on the other end. But either one of these you would want to bring in, generally in real world, you want to bring in a library to do it for you. Right? You're going to be playing around with XML tomorrow in lab, just outputting to XML, not processing XML. That's the hard part, bringing in an input file in XML format and then processing that. But you will see how it's done later on with a library that we bring in. Alternatively, you can have plain text files that are not, none of this stuff is intended for human consumption, right? This is somewhat readable, right? You can kind of understand this. This is a little bit more readable because you've got the opening and closing tags and everything's marked up. Everything has semantic meaning. That this string right here represents, well, what does it represent? The title. This single character here, what does it represent? It represents the title, right? What does, let's see, what does this represent? Well, it represents a para, which is probably a paragraph of some sort, right? Et cetera, et cetera. You have semantic meaning. You can kind of read it, but would you want to read something like this? No. This is intended for EDI, electronic data interchange. It's intended for another computer to speak to another, a computer to speak to another computer and transmit data in a universal format. Even less readable would be base64 encoding. Maybe you can take a human-readable string here, like, hello world, how are you? And then you can encode it as something that is completely unreadable, right? Basically, what you've done is you've taken ASCII text and you've encoded it in base64. Base 2 is going to be 0 and 1, right? There are two things to represent that. Humans count in base 10, right? Decimal, right? You also have hexadecimal, which is base 16, and I've run out of fingers now. But you can also go up to base 64, where you've got 64 characters to represent binary strings. That's going to be all the uppercase and lowercase letters. That's 52 total. 0 through 9, so that's 62 total. And then two special characters. I think that they're right here. I don't think that forward slash, I don't think that's it. But there are two other special characters that are used in base 64 encoding to give you 64 characters instead of just 2, binary, 10, decimal, 16, hexadecimal. You can go up to base 64. And it's just a way of taking, usually base 64 is used to take, say, an image, express it as plain old ASCII text, something that any terminal will be able to read, right? Because it only has those 62 or 64 characters that are in the ASCII character set, and then transmitting it over, say, email or something like that. Base 64 encoding allows you to take binary and represent it as text. It's not readable text, but you can do that so that you can transmit it over a protocol that only understands text, such as SMTP, Simple Mail Transfer Protocol. Everything else ends up getting sent out over the wires as plain text with email. In fact, you can send somebody an attachment, an image attachment, and then look at the raw email. Like in Gmail, you can look at original and see what kind of encoding was actually used. And you'll see that it's just a bunch of garbage text, but it's all text. And none of it is binary. Okay? So all of those are files, plain text files or binary files. Binary files tend to be a lot more compact, and you'll see that tomorrow in your lab. But we're going to stick with plain text files for this course, other than the demonstration that you'll look at tomorrow. The three basic steps are you open the file, right? You process the file, and that could be processing for you're doing file output that you're writing to the file, or you're doing file input, you're reading from the file. And then the third, it's not the most important step, but it's as important as the other two steps is if you open up something, you got to make sure that you close it. 99 times out of 100, the program, the operating system will save you from yourself and close the file automatically for you. It's that 1% of the time that you don't close the file and then it gets corrupted. So always make sure that if you open a file, you also close it at the end. Okay? So how do we do each one of these things? Well, let me go ahead and there we go. So opening a file in C. Right? So how do you open a file? Well, there's this nice little function in the standard input-output library called. Well, first of all, how do you represent a file? A file is represented by a file star. Right? So what do you think that stands for? What does a star mean? Anytime you use a star, what is that? What is that thing? That is a pointer, right? So when you open up a file, where does it initially point? Here's my file, right? Here's the beginning of the file. Here's the end of the file. If you open up a file, you need a pointer to point to that file. It's always going to be starting at the beginning of the file. As you read through the file, you're doing file input, say, or writing to the file, you are moving that pointer through the file. You're starting at the top of the file, reading line by line or character by character, however you're doing it, and then you're eventually getting down to the end of the file, right? And there's a special way that you can tell that you're at the end of the file. It's called EOF. What do you think that stands for? End of file, exactly. But a file is represented by this file pointer. It is all caps. It's standard. It's built into the standard library. I think it's in the standard library. Not that it might be in the standard input-output library. I'm not sure. So to open a file, you use the fopen, or we just simply like to call this fopen, right? File open function, right? And I believe that that is in the standard input-output library, but it doesn't matter. You're always including the standard input-output library. You're always including the standard library, so it's going to be in there automatically anyway, right? Fopen takes two arguments. The first argument is going to be a string representing the path to the file you want to open, right? And we'll talk about that in a little bit more detail here. And the second is a string representing the mode, right? So there are several modes that are supported. We're only going to look at two of them. The first mode that you would want stands for R, and I wonder what that stands for. And the second mode that you would want is W. So what do you think those two stand for? R and W. They're two of the three R's. Reading, right? In other words, file input. And W stands for writing, file output. You're writing to a file or you're reading from a file. And you can do both. You can do things in binary. You can do open things up to append to a file, which means that it's going to start at the end. Don't worry about those. We're not going to cover. We're going to keep it simple. We're only going to be looking at reading and writing. Okay. So let's go ahead and take a look at some examples here. So let's open up a file in the current working directory. Open a file in the current directory for reading. So I would call fopen. Right? And let's go ahead and just open up a file called data.txt. Right? As many of you have witnessed, the extensions don't matter, don't mean anything in Unix. There are conventions where txt stands for a text file. CSV would stand for a CSV file. But more or less, they're not hard and fast rules. In Windows, if you name something .exe, it means that it's an executable, and Windows will try to treat it as an executable, even if it's not, so that it can restrict your access and restrict what you're doing with the file. That's a little bit less meaningful in Unix, but you still should follow those conventions. TXT is a plain text file. We'll open it up for reading. Yeah? right? We usually only give it one character because you can't, for other things like R plus, there's R plus, append plus, or reading and writing, right? If you want to do multiple things, that's why it has to support a string, but we will only ever be giving it one of those two letters. So if I want to open this up for reading, I would give it R, right? Now, it returns a pointer to the open file. So what we need to do is we need to capture that pointer. File, I'll just call it input file, is equal to open. Right? And it'll open up the file and give you a pointer to the beginning of that file. And we'll talk about some edge cases here in a second. But let's go ahead and open a file in the current directory for writing. What would that look like? Well, should I call it input file? Probably not. I'm not doing input with it. I'm doing output with it. Output file is equal to a call to open. And the first one will be a, I don't know, output.txt. That's the file that we'll open up for, and we'll start writing to it. And if I'm going to write to it, then I need to provide it with a W instead. Right? So also same function, two different ways of using it. You do open up something for reading or writing. Right? You can also use relative and absolute paths. So for example, I'll just go ahead and open up F now. I'll go ahead and go with open. And if I want to open up a data.txt file that is 2 levels up, what do I need to write for reading, say? If I want to go 1 level up, what do I use in the Unix file system to go 1 level up? ... right? /. And if I want to go 2 levels up, then I can go another ... /, and then data.txt. Right? You can also use relative. So this is a relative path, 2 levels up from the current directory. Right? And the current directory is always dot, so ... /. When you run a.out, you use ... /a.out. You're specifying that the a.out that you want to run is in the current working directory. You can use an absolute path. For example, let me go ahead and open up the etc password file. Etc password. There we go. For reading. So what do you think is stored in the password file? Passwords? They used to be that way. Thankfully, they changed it. User information. etc stands for etc. People in the Unix world usually pronounce it etc instead of etc. They just call it etc. And then in that there is an etc password file that you can read it. Right? In fact, let me show you. What's in that file right now? Let me go ahead and go to to CSE because my own machine doesn't have. Well, my own machine might have an etc password file. Yep, there it is. Right? It's a user database, but it's my computer, so there aren't any other users here. These are just these users are nothing more than processes that are stored on my computer. Let's actually go to CSE here and see who's in the etc password file. All right? Lots of people. Every single one of you has an entry here somewhere. Right? I won't call anybody out, but let me go ahead and just grep from grep is GNU regular expression. Let me look at my entry. Right? Oops. Got to spell my login correctly. There we go. There I am. Seberg, and then this mysterious X here. That's my user ID. That's my group ID for faculty. There's my name, comma, my office number, etc., comma, and then there's my home directory and my default shell when I start up. Right? Now this X here, what do you think that is, or what do you think it used to be? In the very early days of Unix, that's where passwords are stored. They're not stored there anymore. Right? Clearly, I have permission to read this because the passwords have been moved somewhere else. Right? They've been moved to a file called the shadow file, the etc shadow file. So that's going to be etc shadow. Right? The etc file, the password file is casting a shadow, and that's where the passwords are stored. Do you think I should be able to look at that? Now they're going to be encrypted, right? So they're going to be hashed passwords. So it's not like I'm going to read that your password is 1234. But if I could see hashed passwords, do you think I should be allowed to do that as a regular old user? Nope. Permission denied. Because you do not have permission to read this file. That's one thing that can go wrong, right? And there are a couple of other things that could go wrong as well. Right? But for now, understand that, yeah, you can go ahead and read this file up here. don't worry, the passwords are stored somewhere else. And another observation here, is this a CSV format? No, what is the delimiter here? How is each one of these fields delimited? With a colon, right? So it's still a CSV file, colon separated value file. We don't usually use that term though, all right? But you can use absolute paths where if it starts with a slash, a forward slash, that means that you're going all the way to the root. You're going all the way up in the directory hierarchy, and then you're going down, right? Relative paths are from where I am, go forward, go down in the hierarchy, or go up in the hierarchy. Absolute paths means that you start at the top of the hierarchy and you work your way down, okay? Of course, the file opening can fail, right? Opening a file may fail, right? And one of those failures, what could cause one of those failures? Permission. Permission may not be available to read or write to a directory, right? The file may not exist, right? Usually, it will be created for you, right? So if you open up a file for writing, then, okay, it'll create the file for you as long as you have permission to do so. If you open up a file for reading and it doesn't exist, I wonder what happens. All right, but in any case, if a file opening fails, then fopen returns what? What's the only thing that it can return since it's returning a pointer? What's the only thing that it can return to indicate failure? Null, exactly. Right. Which you can check for. You can thus check to see if a file opening failed or succeeded. How would we do that? Well, let me go ahead and write some simple code here, right? Let me go ahead and try to open up the Etsy shadow file and see see if it works. Etsy, not password, but shadow. Shadow, there we go. And you can check it. If f is equal to null, then printf failed to open file. Or we'll go ahead and go with an else here. Else printf, you may start reading, writing, whatever you're doing with the file, right? And fix that. And I'm actually going to take this over and in our demo file, I've got a demo running over here. Let's go ahead and try it out, right? Let me see. Do I even have an Etsy shadow file? More Etsy shadow. There's no such file or directory. So let's see if this works. This is just a dummy text file over here where I'm trying to open up the Etsy shadow file. It doesn't exist. So what's going to happen? GCC file demo. There we go. So if it doesn't exist, did it fail? Failed to open file because it doesn't exist. That would also fail if you didn't have permission to open the file, like on CSE. You don't have the permission to open that file. But what about the shadow file? Let's see, password file. I should be able to open that up, especially if I can look at it from. I looked at it up here, right? So I should be able to look that up and see that it works. Oops. Yep, you may start reading or writing. So a file opening may fail or it may succeed. You need to check to see whether or not you got a valid pointer back or if you got null back from the opening. Okay? All right. Let's see. In general, if you open a file for writing, it will be created for you. In fact, if a file exists and you open it for writing, what do you think will happen? So I've got this nice file here with a bunch of text, my first novel or something like that, right? I've never written a novel. I don't care to ever. But I've got poetry there or something like that, and I want to open it up with the C file and start processing that. Well, where is it gonna start opening? Well, here's my file. If I open it up for writing and it already exists, and I start at the top and I start writing, what happens to all that old stuff? What happens to all my poems that I wrote? what's going to happen to them? You're overwriting them. So you've got to be careful. If a file exists and you open it for writing, its contents will be overwritten. Right? And there's no undo button. Right? If you, there's no Control-Z button to undo. There's no undelete button. There's nothing like that. You need to make sure that you're absolutely careful that if you open up for writing, then whatever is there before will most likely to be destroyed. Now, there are ways around this. You can jump to the end of the file. It's called fseek. You can fseek, file seek, and you can jump to the end if you want to. I'm not going to cover that in detail, but there are ways around this so that you can preserve and then go to the end of the file and start writing from there instead. Okay? Again, so let's jump to the third part here, closing a file. Right? Once you are done processing a file, so that meaty part, that middle part where you actually have to process the file, we'll come back to that because closing a file is simple. Once you're done processing a file, you should close it. Failure to close a file may lead to file corruption. Right? Even if you've written, say, a megabyte of stuff and you don't close it, there's a 1% chance that that megabyte that you wrote, maybe half of it will make it out to that file. Maybe none of it. Maybe in the middle of the sentence that it'll actually make it out to the file. You actually have to do what's called a flush. You're flushing a buffer. But closing the file will take care of that for you. Right? So failure to close a file may lead to corruption. Right? To close a file, use the, what do you think our function is called to close a file? Close, right? But there's something else with it. What are you closing? File, so close, right? And you pass it the file pointer that you want to close. Attempts to read or write after a file is closed are our old friend undefined behavior. Right? So don't do it. Here's an example. So suppose that I did what I did up here, that I've got this Etsy shadow, and I'll ... to do process the file. And we won't open the shadow because, of course, we weren't able to. So let's go ahead and say that we're opening up the password file. To do process the file, now close the file. And to do that, it's just simply close, and you pass in the pointer. Right? You don't pass in the string that you opened it up with. You were given a pointer. Sometimes that's called a handle. And so sometimes in some examples, they'll use H instead of F. I'm using F here to stand in for file. So H is also the next letter, so E, F, G, H. I guess G would be next. But sometimes people use H because it's called a file handle, right? It's handling the file. But for close, we'll close it for you, okay? So let's take a look at file output first of all. This is plain text output, right? So there are many ways to do file output, that is, writing to a file. We're going to focus on one. So you all remember printf, right? And everything that you know about printf can now be copy-pasted. It's okay to copy-paste knowledge, and just not code, right? Everything that you know about printf is now applicable to file output because all you have to do is put an F in front of it. Right? And everything that you've done with with printf, the %s, the %d, all of the modifiers, so %10.2f to do everything with floating point numbers, that's all applicable, and it all works with file fprintf as well. Right? But fprintf it takes the file pointer as the first argument. Then the usual arguments follow. All right? So as an example, let me go ahead and open up a plain text file. File f is equal, or output file, let's say, output file is equal to fopen output.txt. Right? And we'll open it up for reading or writing. If I'm going to do a file output, I'm going to be writing to it. So I can also check to see that do I actually have permission to do this. If not, don't continue. I'll go ahead and leave that as an exercise for you, though. Now I'm going to want to print several things to it. So let's go ahead and create some variables. Int x is equal to 42. Int pi is equal to 3.14159. Char name is equal to Chris. There we go. And anything else? Char initial is equal to, let's say middle initial. My middle initial is going to be M. Now let's go ahead and print all of that out in some standard format to the file. Normally we would use printf, right? X is equal to %d for an integer. If you want to, you can format it as pi is %10.2f. We'll only go out to 2 decimal places, but we'll print a minimum of 10 columns, including the decimal place here. So it's going to print a bunch of spaces. We can put in tabs and end-line characters if you want. I'll end the line and tab over. You are %s for the string and %c period for the initial, and then we'll end the line there. And then all we need to do is give all of this stuff to as an argument list, pi, name, and mid init. Right? There we go. Now the only difference here is if instead of printing to the standard output, you're going to be printing to a file. Now you need to provide which file are you going to be outputting to. Well, I'm going to be outputting to the output file that I opened up previously. And of course, you have to open it up before you do any output or input for it. It's ordered. You have to open it up, then process it, then close it. So once I'm done, you can also print hard-coded stuff. Printf. Hello world. How are you? And then end the line. Right. Then we'll go ahead and close it. For close, output file. Oh, and then I need to put output file up here as well. Right. There we go. Let me go ahead and take this code and move it over here to our demonstration again. And I'll go ahead and get rid of that and see it in action. Right. First of all, let's see, where am I? I'll get off of CSE there, so I'm making sure that I'm at the correct one. More output. OK, so you can see that there's no output.txt file yet, right? It's going to create one when I open it up and start writing to it. Yeah?
For your pi, you have it declared as an int.
Oh, sorry. Thank you. Double. There we go. Still would have worked, though, right? It just wouldn't have. It would have been 3 instead. Let's go ahead and compile this again. Oops, and I forgot my semicolon, too. But the compiler was smart enough to figure that one out. All right, let's run this. And you see, no news was good news. It opened up the file, it wrote to it, and it closed it. I didn't print anything out to the standard output, right? It was all fprintf. But you see now that this file has now been created. There it is. It wasn't there before. If I ask the system what kind of file that is, right, that's an ASCII text file. If I ask how big it is, well, it's 68 bytes. So I must have written 68 bytes there, right? 68 characters. And if I look at it, well, there it is. X is equal to 42, pi is, and then a bunch of spaces, 3.14, only 2 decimal places. And then a tab over here. And tab is, wow, tab is 1, 2, 3, 4, 5, 6, 7, 8 spaces over, apparently, in this terminal. And then you are Chris M. And then, of course, I had that hard-coded line right there. Right? All right, so that's plain text output. Just use printf. Everything that you know about printf, all the tricks and tips that you've got with printf, you can now use with fprintf instead. Okay. File input isn't so. File input is not so easy. You can't. There is an fscanf. Do not use it. Right? And there's good reason not to use it. In fact, the documentation tells you not to use it because you are risking buffer overflows. So file input. That is again plain text files. We're going to look at two ways of doing this. Right? There are many ways to do file input. Right? Most of them are extremely dangerous. In fact, if you look at the man pages for some of these, they will say, do not do this, right? Because you're risking a buffer overflow. So what I mean by that is if you're reading in, like the standard input, if you're using fscanf and they sit there and mash the keyboard, right? Scanf, that stands for scan formatted. If somebody is just sitting there mashing the keyboard, they're not formatting according to your assumptions. Likewise, you have no control over what somebody puts into a file. So there's no formatting that you can enforce, right? You're at the whim of the user, so don't do things that don't, put some limitations on the number of bytes that you're reading, okay? Most of them are extremely dangerous. But we'll focus on two safe versions instead. So the first one that we're going to do is fgetC and fget s. Right? So we call these fgetC because there's no way of nicely pronouncing that. But fgets s has a nice pronunciation. Forgets, right? So use forgets. Right? fgetC. What do you think that stands for? File. That's pretty obvious because everything that we've been doing right now has an F in front of it for file. Get, well, okay, that means that you're getting something. C, what are you getting then? A character. Gets a single character from the file and advances the file pointer to the next character. Right? It actually returns it. It returns it as a. In other words, i.e., this function limits input to 1 byte at a time. So that's always going to be safe. It actually returns an integer, I believe, technically, but you can treat it as a single character. You can always typecast it as a character and it'll be safe. Because there's, as long as you're reading an ASCII text file. If you start reading Unicode, right, with a bunch of Chinese, Japanese, Korean fonts in there, good luck. Right? It's going. Most of those are going to be 2 bytes, and so you're going to be reading 1 byte that has no interpretation and another byte that has no interpretation, and you'll just get all these squiggly lines and stuff like that. Usually they manifest themselves as these diamonds with question marks in between in them and stuff like that. So you'll just get garbage if you start reading a non-plain text file or even a Unicode file. If you go to Word and they've got these special characters, like the quotes in a Word file are special quotes, right? They're the curved ones. If you go and try to cut and paste that to a regular file, the Unicode will be pasted, and a plain old file reader like C will not be able to read those things. Yeah.
Yeah. So if it advances the file pointer, does that mean if you wanted to go back to the beginning, you'd have to redefine it?
You'd have to rewind, and guess what you use for that? There's a rewind function that you can use. There's a rewind and a seek. You can seek to the next thing, and all of these words were chosen way back when. What was the storage medium, say, 40 years ago? You had hard drives, yes, but the main storage medium was? Oh, say what? Even before that. Tape drives, exactly. So tape drives, you can fast forward tapes. You can seek tapes, right? You fast forward. You can rewind tapes. And that's exactly why these words were chosen. And so we're still living with them to this day. Right? But you can do that if you want to. So let's go ahead and look at an example. Right? But before we do that, we have to know when we get to the end of the file. fgetC returns a special character. And it's not really even a character. It's an internal representation, usually -1. Because if you look at the ASCII text value table, there's no negatives. So usually this will be represented as a -1 or some negative value that you can test for. Returns a special character, and that's why I'm putting it in quotes there. It's not really a character, called EOF when it gets to the end of a file. Right? EOF stands for end of file. Right? And it is caps. It's defined in the standard library. So let's go ahead and go over here to this file demo. And let's go ahead and read an input file now instead. So I'll change that to, I've got a file set up already here, data.txt, with just a bunch of stuff in there. So let's go ahead and open up that file, data.txt. Do I want to open it up for writing? If I did, I would be overwriting all this wonderful data over here, right? I would be getting rid of it, and I don't want to do that. I want to read that data. So we're going to read that file. Right? Now, I can read this one at a time. Char C is equal to forgetC input file. Right? And I can go ahead and print it out. Printf, read, %C, and the line. Right? and then I can do it again. Let me go ahead and copy paste this, copy paste. So I'll read the first 3 letters in this file. And let's go ahead and compile this and see it in action. Oops. What do I need to do if I want to print it out? C. There we go. You only get that with the WAL flag on CSE, so make sure that you're always doing that. There we go. And now it's fine. So HEL, all lowercase. And that's because that's what's in this file, HEL. So if I wanted to do this, but I wanted to read every single character in the entire file, then what would I need to do? I would need to go into some sort of a loop. And do we want to do a for loop or a while loop here? Oh, probably a while. Do you know how big the file is up front? No. There are ways of finding that out, but I'm not going to cover them because they require FASIC and rewind and stuff like that. So while some condition, what I'll do is I'll print out what I've read so far and then set up my loop for the next iteration by reading the next character in the file. Right? And I'll read this character by character by character. Okay? Now what's my condition here? When do I keep going as long as it's a valid character? I keep going as long as it's HELLO space WOR dot 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 dot. Eventually when I get down to the end here, forgets is going to return what? When do I stop? When it's equal to end of file, right? And so while it's not equal to the end of the file, keep going, right? The moment that it's equal to end of file, that is, I read the next one, I'm going to jump out of this loop and be done with it, okay? So let's go ahead and run this, and you'll see that it actually read every single one. Hello world, how are you? Computer science is fun. YTMND, and last line, right? What was the last thing that it read? That exclamation point. What was the last thing in the file? That exclamation point. EOF is not part of the file. That's a system indicator that says that you've reached the end of the file. There are ways that Unix represents the beginning of the file and the end of the file, usually using metadata and stuff like that. You don't have to worry about that low-level file system details. Okay? Well, that was nice, right? I could read a file character by character by character by character, which is really, really inefficient, though, right? Because, in fact, the most expensive thing that you can do in computing is file I/O, reading and writing to a disk. Because even if you've got a solid-state drive, reading and writing to a disk is going to be orders of magnitude slower than reading and writing from memory. So you try to do as much stuff in memory as you can. In other words, if you have to stop each time that you need to read the next character, that's going to cost you in computation cycles. Instead, what I want to do is I want to read an entire line at once. Or maybe I want to write a file that write a function that will read an entire file all at once. That you're going to do in hack, right? But before we get there, I'm not going to give you the answers to your hack, but we will look at ways of maybe implementing those things. So I'll go ahead and make sure that that's included in your notes. Alternatively, you can read an entire line at once using the other one, forgets. Nope, forgets. There we go. All right. So forgets, what do you think that stands for? File, get, that's the same. S, string. It gets an entire string at once. Right? Forgets gets up to the entire string, line, at once. I don't know why it's code highlighting that stuff, right? But you provide it several arguments. Right? So the several arguments are going to be, let's see, where is it? Yep, here, I'm going to cut and paste the signature here. Forgets the character S, the size that you want to read, and the file stream, the file input, output, they're usually designated as streams, file streams. So it takes 3 arguments. The character S, that's going to be the destination string that the line in the file will be stored in. So, caveat there, your destination string needs to be big enough to hold whatever you're reading. Well, unfortunately, you can't predict somebody that is going to create a file with huge lines. Maybe an entire megabyte of DNA data with no end line characters. So you've got an entire one line, but it's a 1 megabyte line, right? You can do that. It's just very, very long and very, very inefficient. But you can't predict how long each line is going to be. That's where the second one comes. That's where the second argument comes in, right? The second argument limits the number of characters written or to be read to size minus 1. Oh, why minus 1? If I'm reading a bunch of strings, say of 5 characters, right? How big of a string do I need to store that? 5? Nope. What? 6. Why that 6th one? The null terminating character. So I'm going to tell it read 100 characters. It's only going to read 99, anticipating that it's going to need to put that null terminating character in there for me, because it includes the null terminating character for you. Nice. I don't have to do that work at least. Right? The third argument is the file to be read from. Right? Now the way that this works is forgets will read up to size minus 1 bytes. That is characters. Now, not always, but you can pretty much have a one-to-one correspondence between characters and bytes because C uses the ASCII text table. Right? Forgets will read up to size minus 1 bytes or stop early if it encounters the end line character. So if you've got usually you set up a buffer, say a buffer that's large enough to handle any line that you might be processing. And then you read line by line by line. And if that buffer is 100 characters, and the next line is only 5 characters, it doesn't read the next line, next line, next line until it fills up this buffer. It only reads at most 100 characters, stopping at the first end line character, and that's what you actually read. All right? So let me go ahead and go back over here, and let's do the same file, but we'll do it as a forgets instead. Right? So I've got the same file here, and what I'm going to do is I need to set up a buffer. So let's go ahead and create a string, char. I'll call it buff for buffer. I'll set it 100 because none of these lines is more than 100 characters long, right? So that's going to be our buffer. Now, if you do have a use case where you're going to have very long lines, then you need a better solution, more robust solution, less fragile solution, where you would read if you've got a very long line, you'd only read a chunk of it at a time until you get to the end. But for simplicity, we're going to keep it simple, and we're going to just assume that no file here is more than 99 characters because of that minus 1. If that's not operable, then go ahead and do 1,000. Now you'll note here that I'm doing something I told you not to do, static arrays. Right? It's okay with a buffer because it's temporary, it's small. This is exactly the use case that you would want to use a static array with. But if you're going to read an entire file and hold that in one big giant string like you're going to do on Thursday, that needs to be a dynamic string. Okay? Where you go through the file, count up the number of characters that you need, dynamically allocate it, go through the file again, and read it all into that one big giant string. Okay? So there's my buffer. Let me go ahead and read the first line. Forgets, and remember that it takes 3 arguments. The first argument is the string that you want to read into. The second argument is the maximum size, minus 1, that you'll read. And then the third one is going to be the file. So in this case, that's going to be, I want to read it into the buffer. I want to read at most 100 minus 1, so 99 characters. And I'm going to be reading from the input file. Oops, let's go with 100 right here. Right? Typically, the reason that it's 100 minus 1 is so that if you've got a buffer of a certain size, you don't have to manually do minus 1 every single time. It does that for you because it's going to take care of that null terminating character for you as well. So let's go ahead and print this out. Printf line is equal to %s end the line. In fact, usually sometimes we call these lines instead of buff, but I'll just go ahead and keep it as buffer. And we'll print out the buffer. Right? And let's see this in action now. There we go. And what's the first line? Well, it's hello world. Right? Let's do this again. Let's get the second line. Well, copy, paste, copy, paste. Second line, third line. And when we do this, well, we get the second line and the third line. Remember over here in data.txt, the second line was, hello, how are you? The third line was blank. But immediately I see a difference. What's that difference? What do I have after each one? I've kind of double spaced. I've got 2 end-line characters. Why? Let's come back over here to our file, to our source file here. And what am I doing? Every time I read a line, right, that line has an end-line character in it. Right? There's an end-line character that goes to the next line, an end-line character that goes to the next line, an end-line character that goes to the next line. That's still in the buffer. It retains that end-line character. And so when I print it out, this string right here has an end-line character. And if I print another end-line character, well, then that's why I've got 2 end-line characters there. What if I don't want that? What if I want to read in each line and I want to remove that end-line character? What could I do? After I've read it, how do I get rid of that end-line character? How could I get rid of the last character in a string? Okay, replace it with a null terminating character. Which one is it, though? Is it 99? Always? No. Is it 10? Not always. How do I know where the last one is? String length of the buffer. If it's 5, if it's of length 5, right, and then here's the end-line character. That's at 0, 1, 2, 3, 4. So what do I need to do? -1. And let's see that in action over here. Oops. Semicolon. There we go. And there. That's sometimes that's called chomping. You're chomping out the end-line character. You're chomping, in general, you chomp out trailing white space. You chomp out leading white space. Right? So it's important to understand that the end-line character is retained. Forgets retains the end-line character. You need to manually remove it if you don't want it. All right, well, that's good for reading line by line by line by line, except for I want to read every line. I want to read all the lines in the entire file until I get to the end of the file. Okay? Forgets operates a little bit differently. Forgets returns, since it returns I didn't talk about the return type yet, but forgets returns a pointer to the string that is a char star that it read. Right? So when it reaches the end of the file, it returns what? If it returns a pointer, what's the only pointer that tells you you're done, it's invalid, it didn't work? Reading the next line didn't work. So I'm going to return null. It returns null, which can be checked. So let me go ahead and modify this code to read the entire file line by line, read the entire file line by line until the end. So we'll probably want another while loop here. And I'll go ahead and forget the line, chomp out the end line character if you really want to. I'll go ahead and leave that in there, but comment it out for now. And then print it out. There we go. Instead of just doing it once, twice, thrice, I'm going to do it all the way until I get to the end of the file. Now to do this, what do I need? I need a pointer, first of all. Char star s is equal to null. I don't know. How are we going to initialize this? So we'll come back to that. And then we'll need to capture that line reading, right? So we're going to capture the line reading, and as long as that's not null, you've not reached the end of the file. Keep going, right? What do I initialize it to make sure that this actually runs? I could initialize it to 1, but is that safe? No, that's some random memory location, right? I couldn't initialize it to not null. You can technically do that. Don't do that, right? I don't know. You could probably, let's see what happens. I'm curious. Okay, yep. It's just a warning, so, but it looks like it worked, right? But, well, it actually didn't work. I've got that last line twice. And that's because I probably need to rethink how I'm doing this. What I'm going to do is, what if the file is completely empty? Will this work? Well, no. I mean, it'll attempt to get a line and then probably print it out. So what I want to do is call it once at least, right? Now, if the file is empty and it immediately returns null, telling you that there's no line to read, then this while loop never gets executed. The print statement never gets executed. Right? But now this presents a problem. Let me go ahead and show you what the problem is. So how are you? Do we get the first line? Remember, the first line is hello world. We missed the first line. What do I need to do to this while loop over here to ensure that I get that first line? I need to print it first. Right? So read the line, process it. Set yourself up for the next iteration by reading the next line. Right? Then it goes up to the top. It's still not null, so you're still in the file. You're still reading the file. You're still doing file I/O until you get down to the end. Now this one should work. Right there. Hello world, how are you? No, an empty line. Computer science is fun. YTMND with the period. Or did I have a period in there? Yes, I did. And then last line. And it reads all the way to the end. All right? So there is a very simple for loop that reads an entire file line by line with the assumption that no line is more than 99 characters long, including the end line character. So do not, at this point, do not confuse the end line character with the with 0 or the null terminating character or null. You have 4 different things that kind of mean similar things now. Make sure that you're using them in the correct context. Okay? I'll go ahead and make sure that this is in the notes over here. And review that, str or forgets return. Oh, I think we already did that up there. Yeah, it returns null at the end of the file. Okay. All right. So, any questions on that so far? Like I said, it's going to be short because a lot of the stuff that you've already encountered is applicable to file I/O. The only place that you have to be careful is file input, because the same stuff where people can mash the keyboard, you have to be careful because they can write corrupted files. They can write garbage files, right? And if you ever, you got to be careful here because you don't want buffer overflows, and so always use forgets, right? All right, let's see, anything else? Oh yeah, chomping. Remember that forgets always retains the end line character if it encountered it. So you can chomp it out by setting the end line character, which is the /n, to the null terminating character, which is /0 instead. So 2 different things, 2 different contexts. Be careful. I'll wrap it up here by talking a little bit about binary data in C, because you will see this tomorrow in lab, but only as a demonstration, that binary data can be a lot smaller, right? C provides 2 functions to do binary I/O. Right? For read, right, file read, and you're doing binary input. This is binary input. And for write, for binary output. Oh, sorry, output, for writing, right? Both of them have almost virtually the same signatures. Let me go ahead and bring that over here for you. There we go. Don't worry about the return type here. But for write, what you have is a pointer to the thing that you want to write to, the size of the things that you want to write, the number of things that you want to write, and then the file stream that you want to write to. Okay? So we're not going to be expecting you to do file input and output with binary data. I do want to show you what it looks like, though. So what I'm going to do is I'm going to create an integer, several integers here, an array of integers, say 2, 3, 5, and 7. Well, how big is that? There are 4 things in that array. What I want to do is I want to write an entire array to a binary file. Right? So first of all, I need to open up a file for writing. Right? File, f is equal to output file. And that's a call to, sorry, what am I doing? Fopen, right? And I'll just say output.bin. And bin is just going to be an indicator that it's going to be a binary file, right? And I'm opening it up for writing. I'm going to do file output. And what I want to do is I want to dump that entire array to it, right? So I'm going to go ahead and call for write. And I'm going to cut and paste the signature because I never remember the order over here. There we go. So the pointer, the first one is the pointer to the thing that you want to write. It's a pointer to the thing that you want to write. So in this case, it's the array. And an array is always its own pointer. Right? If you did this dynamically, it would be int star arr, and then you'd call malloc, and then you'd fill the array. I'm just taking the shortcut here of using a static array for demonstration purposes. Now, this one is the size of each element that you want to write. Each element is an integer. So what is the size of an integer? How do I get that? Size of int, just like malloc. That returns the number of bytes in each thing that you want to write. How many things do you want to write? Well, there are 4 of them in there. That's why I put it into a variable, so I didn't have to. So I could come up here and change it if I wanted to. And then finally, the file output that the file that you want to write to, f. Now to close it, for close, make sure that you close it. Otherwise, again, that 1% of the time it's going to be corrupted. Let's go ahead and run this now. GCC. There we go. Now, before I run it, do you see an output.bin? No, you see an output.txt. Right? So what I'll do is I'll run this. And now there's a new file in here called output.bin. What kind of file is that? It's data. Right? It's no longer ASCII text. Let's try to take a look at it. What does it look like? Right? All those weird things again, right? Well, how big is it? It is 16 bytes. Why is it 16 bytes? 4 integers. How many bytes each? 4. So total of 16 bytes. Right? If I did this in plain text, what would it look like instead? So f is equal to fopen output dot, or numbers, let's say, numbers.txt for writing. And instead of for write, I'll go ahead and say, what is it going to be? Printf for plain old text, %d, 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 %d. And of course, I'll want to put in a space between these two numbers, between all these numbers, and maybe an end line right here, and then array sub 0, array sub 1, array sub 2, and array sub 3. Not only that, but I'm going to change the values up here. Does anybody remember what the maximum value is? 2,147,000,000 and some change, but I don't know what that change is. All right, there we go. We'll do that one, and that one, and that one, and that one. All right. Let's try this again. Oh, and what did I forget to do, by the way? You open a file, you need to do for close it. All right, F. There we go. So let's run this. Oops. %d, what? Nope, numbers.txt is fine. Why is it complaining about this fprintf? Oh, duh. F up here. There we go. Now, I remember I've got to provide the file name. All right, there we go. It's happy. Now, the output.bin, more output.bin, that's still unreadable. In fact, it says it's a binary file. Do you want to really do this? And no, I don't. lsla output.bin. It's still 16 bytes because every integer, regardless of how many digits it has, is still only 4 bytes. Okay? But when I look at the regular output file, let's say, what did I call it? Numbers.txt? Oh, more numbers.txt. It's got a lot more characters. How big is that file? 44 bytes instead. The 44 is right here. Oops, where are we? Oh, 44. Why? Because each digit takes 1 byte to express. I've got other things like spaces to delimit things. If you are writing binary, and this is 4 bytes, this is 4 bytes, this is 4 bytes, this is 4 bytes, you don't need delimiters. You just need a known format that every integer is 4 bytes. So I only have to read these 4 bytes, read these 4 bytes, read these 4 bytes. So in other words, binary files are way more compact, especially, and they're the way to go if you have actual binary data and it is only intended for computer consumption. If it's intended for human consumption, that's when you need to start writing things in plain text. Unfortunately, you're going to be paying for that. If I'm storing, say, 1 million integers, right, then there's a huge blow up in file size and consequently file processing if I'm doing this all plain text versus a binary format, where you can just dump everything with 1 line and read everything with very easily. All right, so that's the difference between binary and plain text. Right? Again, you'll mostly be working in plain text, but you'll see a demonstration like this tomorrow in lab. Right? Any questions on file I/O? No? All right, well then, we'll continue with a little bit of file processing on Wednesday, but otherwise we'll move on to, on Wednesday we'll move on to the next, we'll motivate the next module.